Picture a high-stakes pub trivia game. At one of the tables, there is exactly one person sitting entirely alone. They are trying to win the whole competition by furiously memorizing every single fact in a giant encyclopedia. In data science, this solo trivia player is like a decision tree algorithm. It tries to learn by creating very rigid, logical rules for every single piece of information it sees in its training data. If you map out its thought process, it looks like this growing flowchart. The problem is, when the trivia host asks a question that is worded even slightly differently than the exact text in the book, our solo player freezes up. The rigid rules fail. We call this overfitting. The algorithm has perfectly memorized its past data, but the moment a completely new piece of information appears, the model breaks down. It struggles to make a correct guess on anything it hasn't seen before. You might think the solution is to give the player a bigger book or let the flowchart grow even deeper. But adding more processing power doesn't fix the design flaw. A single perspective is always going to have blind spots. Reliable, real-world predictions don't come from trying to build one perfect brain. If you want to win, you have to build a team. In machine learning, we call this forming an ensemble. Let's replace our solo player with a massive team of 100 people, all sitting together at the same trivia table. They all have different backgrounds, different ages, and different interests. To make this work, the team has one absolute rule. They cannot all study the exact same material. If they all read the exact same book, they will all make the exact same mistakes. Instead of one giant encyclopedia, each person is handed a randomly selected study guide. This technique of handing out overlapping data subsets is called bagging. When asked a question, everyone writes their independent guess, and the team goes with the majority vote. This specific combination, randomizing the study data, training lots of individual trees, and then taking a vote, is an algorithm called a random forest. It acts as a sturdy reliability net. Because the perspectives are so thoroughly mixed, the odd mistakes made by any single person are naturally canceled out by the wisdom of the group. The voting committee is great for reliability, but there is a completely different strategy if you want to push for absolute accuracy. Let's replace the committee with an intense study group that operates like a relay race. Player 1 takes a test, leaving a significant gap in the team's knowledge. Player 2 entirely ignores what Player 1 got right, studying only the missed questions. This chain of correcting previous mistakes is called gradient boosting, repeating until the gap is fully closed. There is a catch. If you let this relay race go on for too many rounds, the team exhausts all the actual mistakes. They become so hyper-focused on fixing tiny errors that they start second-guessing obvious answers, and the algorithm begins overfitting all over again. So you have two great options. Random forests provide sturdy reliability. Gradient boosting provides high-stakes accuracy, the kind of precision needed to win complex machine learning competitions. But an ensemble doesn't run itself. As a data scientist, your job is to act as the team manager. You have to decide exactly how many players to use and exactly how intensely they should study. One management approach is called a grid search. Think of it as testing every single mathematical combination of team size and study intensity on this grid. It finds the best setup, but it can be slow. If you are short on time, you can use a randomized search approach instead. Rather than checking every single dot, you test a random handful of configurations. Usually that is enough to find a strong setup very quickly. This entire process is called tuning. It is how you carefully balance your computer's processing budget against the complexity of the specific problem you are trying to solve. We have one final twist for our trivia game. Imagine the rules change. 90% of the questions are easy pop culture trivia worth 1 point. But a few, very rare history questions are suddenly worth 100 points each. If your team only cares about getting a high overall percentage of questions right, they will just guess the easy pop culture answers every time. They might hit 90% accuracy, but because they ignored the big targets, they will lose the game. This is an imbalanced dataset. It happens all the time in the real world. Think about credit card fraud. You are hunting for a single stolen card swipe hidden among millions of perfectly normal, everyday transactions. We fix this by reweighting the scores. We tell the team a single mistake on a rare category hurts much more than normal ones. Prioritizing rare cases makes the algorithm abandon generic accuracy, instead aggressively hunting for high-value targets. That is how you build a winning prediction model. You use voting for reliability, sequential correction for accuracy, and you always ensure the algorithm's reward system is set to match the true stakes of your business.